Sim on Wheels, Physical World in the Loop Simulation for Autonomous Driving. Evaluating how a self-driving system performs in dangerous scenarios is hard, but it is still necessary in order to ensure we can create reliable self-driving technology that people can trust in any scenario. The existing solutions fail to meet all the requirements of a robust self-driving evaluation system. Off-policy datasets are safe and convenient, but lack real-world physics and are not closed-loop. Real-world road tests have a realism advantage, but have a high cost to set up and can create dangerous situations. And simulation tests, though they are promising, face a sim-to-real gap at both the perception and physics level. In contrast, our proposed solution is a mixed approach that balances both realism and safety. In this paper, we present Sim on Wheels, a vehicle-in-the-loop framework that can safely and realistically evaluate the performance of autonomous vehicles in real-world scenarios. In Sim on Wheels, we physically run an autonomy stack on real cars, but create virtual scenarios by inserting simulated people and objects into the sensor feed of the car in real time. This enables us to evaluate safety-critical scenarios while ensuring safety during testing. We demonstrate how Sim on Wheels works with two real-world video examples recorded from 3 different viewpoints. The background shows the Sim on Wheels simulation, while the bottom videos show the driver's perspective, a third-person view, and a bird's-eye view animation for the car and obstacles. This test scenario involves multiple jaywalkers running across a road with an autonomous agent controlling the car. At this point, the car is able to brake and successfully avoid the collision with the jaywalkers. Here's another case that tests a scenario with jaywalkers that are initially occluded by the walls on the left, making this a more challenging case than the previous one. At this point, the car tries to brake, but it still collides with the running pedestrians and results in a failure case. Normally, this kind of testing would be dangerous and unethical to conduct in the real world. However, Sim on Wheels guarantees safety during this kind of evaluation. What's happening behind the scenes in these videos is our rendering pipeline. We take a sensor image as input, perform physically based rendering, or PBR, to insert virtual humans/objects into the scene. We blend this render with the background image seamlessly, and finally add in simulated shadows based on the sunlight direction. We also visualize a side-by-side comparison of our autonomy agents in multiple scenarios. First, we have a single jaywalker crossing the road. Now we have a single jaywalker that is occluded by some building walls. And finally, a traffic light violation scenario. Then, to validate the realism of Sim on Wheels, we conduct image level and action level comparison in real and simulated static obstacle scenarios. For image level comparison, we place our rendered 3D object with the same pose and lighting conditions as the real ones, and then quantify the visual difference through reference-based metrics like PSNR and SSIM. Here are the several qualitative example pairs. To further quantify the realism, we additionally evaluate the action level difference by running the same agent on real and simulated input sequences. In both cases, our gem car starts at the exact same position. All of our experiments were performed in a real-world test track on a modified Polaris GEM vehicle equipped with the necessary component for autonomous vehicle development, including onboard sensors, a computer, and a controller. Finally, we showcase that our Sim on Wheels is efficient. Our renderer can support real-time rendering running with other autonomy agents. We do notice that there is a bit of additional latency introduced from ROS message communication, but we hope to resolve this in the future. Thank you for watching, and please check our paper for more details.